Hi, we are the team Colcon Builders, formed by Héctor Castillo and Andrés Méndez.
Our project focuses on the angular velocity control of a DC motor through implementation of a PI controller within the rust-through environment to maintain a desired speed, bridging the gap between digital processing and physical motion.
For the hardware, we use a GM25370 DC motor capable of 330 RPM, driven by a TB6612 F&G H bridge, powered at 12 volts due to its minimal dead zone. The control is handled by an ESP32, and we use the pins 25, 26 and 27 for the direction and speed control, by pulse width modulation. This setup allows us to translate our digital control signals into PWM to drive the motor effectively.
Our software architecture is managed via a launch file that initializes a signal generator, producing a step signal with a 10-second period, ranging from 0 to 4 revolutions per second. The file also launches the micro-ROS agent to communicate with an ESP32, which runs our native ROS node. This node listens to the setpoint topic, enables the motor, and publishes real-time revolutions per second values. For monitoring, we integrated Plot Juggler for data visualization, and a dedicated node to track controller performance via custom messages. Additionally, we included RQT reconfigure to allow real-time tuning of signals and configurations without restarting the launch file. All velocity data is transmitted using standard flow 32 messages.
The foundation of our control loop is the reporting of angular velocity from the ESP32. We implemented an interrupt service routine to count encoder pulses. By considering the gear ratio and pulses per revolution, then we converted these raw signals into real-time revolutions per second. This experimental data is fed directly into our ROS2 network, providing the high-fidelity feedback necessary for closed control loop.
Our first major experimental step was characterizing the process through a static gain test. By sweeping the PMW input and measuring the steady-state velocity, we generated an empirical graph. The results showed a remarkably high linearity, confirmed or nearly non-existent dead zone, and a physical acceleration point at 5.6 revolutions per second. Then, to understand the system's dynamics, we performed a frequency response analysis to build a water plot. Experimentally, we identified the cutoff frequency of 1.78 Hz, and by using the Fadale visual criterion, we determined a sampling frequency of 16.6 Hz.
With this test, we modeled our motor as a first-order plus dead time system. We use the Smith method for system identification, as it provides a superior approximation of the time constant tau and the delay L compared to other heuristic methods. To find the initial control constants, we applied the Chinch-Horn-Reswick heuristic method. This gave us a solid baseline for Kp, Ki, and Kd, moving from an empirical model to a functional data-driven controller.
The final stage was experimental fine-tuning. While the Chinch-Horn-Reswick constant were at the very start, they produced a significant overshoot. We iteratively adjusted the gains, eliminated the constant D as it amplifies the system noise, and we minimized the overshoot, settling time, and the integral squared error. By observing the real-time response in Plot Juggler, we fine-tuned the PI action to achieve a smooth, fast response with low oscillation.
Real-world implementation brought challenges. We encountered significant signal noise, which we resolved by implementing a low-pass filter. We also addressed integration windup using a clamping technique. A key technical observation is that the ROS2 timer period is not perfectly exact, so we measure the elapsed time for every single calculation to ensure the integrity of our discrete control loop. To manage the complexity effectively, the ROS2 launch automated the startup for the entire system with a single command. Also, tools like Plot Juggler, RQT Graph, and RQT Reconfigure were vital for real-time diagnostics, giving us the visibility needed to monitor node communication and fine-tune the motor's behavior.
Our results showed a 12% reduction in overshoot compared to the first concept, with faster settling times. Unlike the simulation, the real system faces physical limits like voltage saturation and a small dead zone, which makes it harder to overcome inertia at very low speeds. However, the closed-loop system successfully compensates for friction, achieving a good performance.
In conclusion, this task highlights the critical importance of integrating ROS2 with microcontrollers. By using micro-ROS, we successfully unified high-level orchestration with real-time hardware execution. This synergy allows us to create scalable control systems, proving that a standardized framework is vital for the development of professional-grade robotics. Thank you.